12th of June 2022 before 5 p.m. today. And let me remind you that you need to submit your project report in PDF format and Octave script source code, because I need to run your code. I need to run your code. Okay, so if you submit MATLAB code and it's not running, so I'll assume it's not running because I do not have a MATLAB on my PC. So please submit Octave. Please submit Octave. Even though Octave and MATLAB use the same .m file, but there are slight differences. Slight differences. So sometimes it will run, sometimes it will not. So please use Octave because I do not have MATLAB on my PC. All right. So the due date is today before 5, and these are some of the. I think this is one of the sample good report. Sample good report. This is the thesis manual and so on. I have everything here for you for your reference. Okay, so what we are going to do today. Okay, by the way, assignment 8 is due tomorrow. I think we talk about it on Thursday. I think you can finish it in about 40 minutes, actually. About 40 minutes, because that is the test question, past test question. So it should be not taking you more than 40 minutes. So it's due tomorrow. And this week, today we are going to start this one, actually, ordinary differential equations. I prepared the video. Okay, I already prepared the videos. And but if you look at the scheduling, we are way behind. We are way behind because today we are going to talk about this, which is the topic for the 22nd May. But we are already at this week, 5th. No, we are here actually, 12th June. But we are still here. Okay, so hopefully we can finish everything before the test. Test 2 is coming soon. So I'm trying to finish this as soon as we can. So please, please watch this video for this week, all these 3 videos. Okay, all these 3 videos this week, because we are going to be a little bit quicker, because we need to finish this topic. All right, so before we start, any question? Before we start, any question? Okay, by the way, today I'm still at home. My doctor advised me not to drive because I have a problem with my eyes. So UTM allowed me to work from home because of the doctor advice. Doctor say, okay, you stay at home, do not drive to work. So stay at home. All right, so now let's start with our lecture, which is this one. So let me stop sharing this e-learning. So let me start. Okay, where is my slide? By the way, you can download the slide from our e-learning portal. So this is chapter 25. Okay, so let's share this. Okay, so this is the slide for my video lecture. So the same slide, I think I'm just going to go through this. You can also watch the video later. So the idea here, today's topic is ordinary differential equation. I think you should know this because you took, I think in your first semester, first year, one of the math subject is this, ODE. I think the Malay word for this is persamaan terbitan, persamaan terbitan. Okay, sorry, I'm a little bit sluggish this morning. Okay, so let's start. So this is chapter 25 in your textbook, ordinary differential equation. So let's see what is the content of this slide. So the first thing is that we, of course, the numerical method always start with math. So mathematical background, Euler's method. These are the method. These are the method that we are covering for this topic. So Euler's method, Hewitt's method, midpoint method, and RK method. And RK method. And the last one is system of equations. It's just the manipulation of either Euler method, Hewitt's method, or midpoint method. That's the idea behind this topic. So let's start with the mathematical background. I think by now, I think you should be familiar with this. This is our Parachutis. Parachutis problem. Parachutis problem. Remember that that guy jumps from an airplane and then he falls down, and because of the drag, it was pushed up and so on. So what we are trying to do, I think, for that problem was to find the velocity. The velocity. So this is the idea. Let's look at this equation. Why is it called a differential equation? Okay, the first thing that we want to know is that we are trying to find the unknowns. So in this case, G is the what we call the forcing function. C and M are the parameters, and V is the parameter or the unknown that we like to find. And note that V appears in two formats. One is V on its own, and then dV dt. So when this unknown appear in two format, one is on its own and in its derivative, then equation which are composed of an unknown function and its derivative. An unknown function and its derivative is called a differential equation. So this is the differential. So look at this. So basically the format here is, you can see that it is just dv dt equal a function of g, c, m, and v. Okay, so let me write it here. A certain function which depend on g, c, m, and v. So this is what we call a differential equation. So that's one thing. Okay, and then the other thing is that when a function involves one independent variable, then it is called an ordinary differential equation, ODE. For example, in this case, our v is only a function of t. So because of that, by the way, this is dv dt, only dv dt. So this is what we call an ODE. Again, this is not something new to you because you've seen this before in your persamaan terbitan. And a partial differential equation, or PDE, involves two or more independent variables. For example, if we are trying to calculate the velocity of a particle in 3D space. So 3D space means you have the X location, the Y location, the Z location with respect to time. So in this case, P is a function of X, location of X, location of Y, location of Z at certain particular time T. So note that our V is a function of more than one independent variable. So in this case, this is what we call a PDE. dE. Okay, so these are the basically identification. So basically, this is what this is saying is that it's just a definition. It's just definition. Uh, it's just definition that what is an ODE. So okay, let's do this. Oh man. Okay. So give me 1 minute here. Okay, so what we have is what we can summarize is that ODE and PDE. So we are going to talk about ODE first, okay, before we go for PDE. So this is an ODE. So what we say here is that this is the form of PDE. Oh, sorry, ODE. So it has ODE, for example, dv dt is a function of x and y. This is one example. Okay, and if you look at our problem, this is dv dt equal to g minus c over m v. So this is the Parachutis. This is the Parachutis problem. And note that our v is only a function of t, so this is an ODE. That's the first thing. Okay, the next thing is that order of the ODE. Okay, that's again, this is not something new to you. This is just definition. So if you look at the next slide, basically, okay, this is the definition. The order, a first order equation includes a first derivative of its highest derivative. For example, dv dt equal to g minus c over m v. Note that the highest order here is d1 dt 1. So this is first order. This is first order. This is what we call the first order ODE. Okay, sometimes you see that this is d square v dt square equal a certain function. Then, according to the highest derivative here, then this is a second order ODE. It's a second order ODE. So a second order equation include a second derivative has its highest order at its highest derivative. So itu saja. So first we know what is, okay, so if you look at this, so we have this differential equation. There are two types, ODE and PDE, and then first order, second order. Again, the same thing for PDE, second order, and so on. So this is first order, maybe second order, and so on. And then the same thing for PDE, first and second order. So this is the definition. It's just definition. This is not new. This is something that you learned in your math class before. So let's look at the next one. So look at this. Okay. So this is first order differential equation, ODE. Note that V is only a function of t. And in this case, theta is a function of t. But look at this. We have d square dt square. So this is a second order ODE. Second order ODE. So again, this is nothing new. This is nothing new. All right. So what we want to do here is we need to solve this kind of equation numerically. Okay, numerically. So what do we do? What do we do? Okay, so the first thing is, again, just like I mentioned last time, in numerical method, the first thing is to approximate. So how do we approximate ODE? Okay, I think we talked about this during first or the second week of class. I think because we started with actually this equation. And how do we do this? How do we do this? So, okay, it says here that for Euler's method, the first derivative provides a direct estimate of the slope. Okay, for example, dv, what is wrong here? Okay, dv dt equal to g minus c over m, c over m v, c over m v. Note that dv dt or dy dx, for example, this is just the slope. And this is the function of the slope. Okay, that's it. So slope and its function. Its function. So how do we do this? I think you've seen this before, right? You have seen this before. So what we can say here is that, for example, in the case of dv dt, okay, dv dt, okay, can be approximated as vi plus 1, or let me do this from the basic. So basically delta v divided by delta t, which can be approximated as vi plus 1 minus vi over delta t, which is ti plus 1 minus vi. So v new minus v old, t new minus t old. And this is just the function of x, y, for example. X, y, for example. Note that we can also replace let h equal to the increment of our time step, which is ti plus 1 minus vi. So we can see that our vi plus 1 minus vi over h is fxy. And then if we rearrange this, you can see that vi plus 1 equal to vi plus fxy times h. Or in general, the formula is just yi plus 1 equal to yi plus fxy times h. Okay, so if you look at this, you can see that this is a new value. This is old value. This is the slope, and this is the increment. Increment. So now, okay, so now we know that this is the function. This is the approximation. This is the approximation. But the question here is, the next step in the numerical method is how do we improve our approximation, or how do we make it? How do we make our approximation has less error, because we want to improve on the approximation. That's the idea here. That's the idea. Okay, that's the idea. So what else can we note that? Note that the only thing that we can change here is h and this and slope here. Okay, I think by now you know that when we make h smaller, our approximation become better. Okay, you can see this during your numerical integration and numerical differentiation, right? This is very clear. So the rest, we cannot do anything. Okay, so how can we improve this? Okay, so we can see that this is the new value, old value, slope, and increment. Okay, so what it says here is that there's a new value of y is predicted using the slope to extrapolate linearly over the step size h. So this is the slope. So for example, this is the example here. Okay, so what we are doing here, because we know what is xi, okay, sorry, we know what is yi, this is yi, right? And this is yi plus 1. Note that, again, our yi plus 1 is based on the old point, okay, the old point, which is this one here, y old, plus, okay, this is new, plus old, plus the slope. So what is the slope? This is the slope. So this is the slope because not that one, sorry, not this one. This is the slope. Okay, this is the slope. Okay, and this is the slope times h. Okay, so our y new is this. Y new. Okay, y new. So look at this. Look at this. That our y new is just basically y old, our known point, plus the slope which is fxy times h. So this is the one. Okay, so this is the one. This is the one. So we have our predicted value of new y. Okay, old y and new y. So this is old y or y old. This is y new. Note that uh, our true value is here, right? And the difference between the predicted and the true value is our error, just like it's written here. Okay, so this is the issue here. But I hope you can see that if I make h smaller, for example, I make my h smaller here. Okay, if I take h here, so this is my h. This is my h. Okay, new h. For example, this is my new h. Look at the error now. So the error now become lesser because this is the predicted value and this is the true value here. See, this is how we improve our approximation. So clearly you can see graphically when we reduce h, it's become, our approximation become better. And of course, if we take h at this point here, this is even closer to the true value. So what is the side effect of this? Okay, when you make h smaller, you need to do more calculation. To do more calculation. For example, if you want to know the value here, okay, if you just use one h from here to here, then it's only one calculation. If you use half of h, then you need to use twice, because you can predict this value, and then you can predict this value. So it's twice. If you only take a quarter of h, the original h, then you need to calculate 4 times. So that is the side effect or uh, the I lost the correct word here. I think that's for now. Let's call it a side effect. So we have to do more work. Yeah. So more accuracy means you need to do more work. That's Okay, so improving approximation. Okay, one is reduce H. Okay, and if you look at the next slide, you can see that this is the original equation, and this is the ODE. It's the ODE. Okay, so now take a look. Our first value. Okay, this is the given value, or this is what we call the initial value. Okay, the initial value. Okay, this is the initial value. So there's nothing we can do about the initial value because we are going to use that. And note that this is H 0.5. And when we use H 0.5, note that our yi plus 1 equal to yi plus f xy times h. Okay, so so in this case, our y1 equal to y0 plus the slope times h. Okay, now take a look that our y1 already has an error here. Our y1 has an error. Okay, already have an error. So based on y1, we are, this is not yi, but this is y1. And then based on y1, we can find y2. And note that our y1 already has an error, and we use this value to find what is our y2. So you are basing your approximation on a value already has an error. So you can see that compared to the true solution and the approximated solution, there's a huge gap between them. Okay, so this is the side effect, or this is the bad thing about Euler's method. So what if we reduce it? Okay, so I think, okay, so let's jump to a few more slides here. Let's see that what if we change our h from 0.5 to 0.25? See that the error has been reduced. But take a look at this. When we use h 0.5, there are only 1, 2, 3, 4, 5, 6, 7, 8 points to calculate until x equal to 4. But when we use h equal to 0.25, the number of points that we need to calculate is double. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Okay, previously it was only 8, but now it's become 14. So you can see that by reducing our h, we improve our approximation. Okay, so that's the idea. So it all comes from, okay, I think I'm going to skip this, but this is in my video. You can watch the video. I think I explained about this. So you can see that, okay, so this is the Euler's method. So we can see that the error can be reduced by reducing the step size. So in this case, yi plus 1 equal to yi plus fxy, which is the slope, times h. So we reduce h, we get a better approximation. If the solution to the differential equation is linear, then method will provide error-free prediction for a straight line. The second derivative will be 0. So in this case, let me show you what it meant here. Okay, so if our true solution is just a linear line, which is y equal to mx plus c, then you can see that our dy dx is just m, and our d square y dx square equal to 0, which means this is a linear line. This is a linear line. So our yi plus 1 is just Okay, it's just, let's say this is our y0. Yeah, this is going to be our y1. So y1 equal to y0 plus, the slope is just m. H can be any number, for example, h, or in this case, this is our x, our x. So this is just the same thing as a straight line. Method is good for a linear line. Okay, but if the line is non-linear, for example, in this case, this is a fourth order line. Okay, this is a polynomial of the fourth order. Then Euler method will give you a lot of errors. Okay, so what we need to do is to reduce h. So this is the idea behind Euler's method. So that's the first step. So we say, okay, in numeric method, the first thing to do is to approximate. Okay, so we know we can approximate using Euler's method for ODE. Then the next thing to do is how do we improve Euler's method? So one way is to just decrease or make h smaller. Make h smaller, and we can see the effect here. We can see the effect that smaller h give you lesser error than bigger h. Okay, so now the next thing to do is what is the improvement? So we started with the very crude approximation, which is just using Euler method. So there are other ways. So a fundamental source of error in Euler's method is the derivative or the slope at the beginning of the interval is assumed to apply across the entire interval. Note that this is one of the issues in Euler's method. We assume this is good for the whole solution. But remember, our first approximation already has an error. And we find the next approximation based on the first approximation that already has a lot of error. Okay, so this is the issue with Euler's method. So this is what it says here. Other than using smaller step h, improving the slope estimation reduces Euler's method error. So we see that one way, what we can do is that this yi, or the initial y, we cannot do anything about it, okay? We say there are only two things that we can modify here. So we tried making h smaller, and we can see there are some improvement. So the other way is to improve our slope approximation. So the Euler's method improvement is one, using smaller step size. Okay. One method to improve Euler's method is to use smaller step size. And the next step is improving the slope estimation. Okay, improving the slope estimation, which is the second approach. So we know that our yi plus 1 equal to yi plus f x y h. So we are done with h. Now this is time to improve this slope. Okay, improve slope. Okay, so in the textbook, it says about there are two methods, which is Hewan's method and the midpoint method. Okay, so these two things are basically trying to improve slope estimation. Okay, so it will try to make our slope approximation better. Okay, so let's see how does Hewan's method and midpoint method improve the slope estimation. Okay, so let's look at this one. Hewan's method. Hewan's method say one method to improve the estimate of slope involve the determination of two derivatives at the interval. So for example, if we have this, So let's say this is our xi, and this is our yi, and let's do this. Okay, let's say this is my line. Okay, this is my curve. Yeah, this is my true value. This is my true value. Okay, so if you look at this, this is just our Euler's method, right? This is just our Euler's method. So look at the slope here. This is the same slope as the Euler's method. So why not let me draw a better one here. Okay, so okay, this is my xi, and of course this is going to be my yi, and let's say this is my curve. Okay, so I want to change color here. Okay, so the first is what we call the, if you take a look at the note, it says that there are two methods here. Hewitt's method, the first thing that you need to do is to what we call the predictor, predict. So we need to predict. So in this case, okay, in this case, what we can do is yi plus 1 equal to yi plus fxy h. Okay, this is what we call the predictor, or basically it's just an Euler's method. So let's say we are going to find what is our xi plus 1, yi plus 1 value at xi plus 1. So this is xi plus 1. Okay, so using the first one, you see that this is our predictor. We predict that the slope is maybe here. Okay, so this is our yi plus 1 based on our predictor. So this is our predicted yi plus 1. Again, you can see that there's a lot of error here. Okay, there's an error here. So now what we need to do is, the next thing is to use the corrector, So if you look at this, it says there are two steps in Hewitt's method. So the first one is to predict. Okay, once we get the value, what we need to do is to make correction. Make correction. Okay, note at the correction or the corrector, this is our first slope, right? This is the same thing as this one. And what about this one here? What about this one? Note that this is the slope at the new point, which is xi plus 1. So basically, the next thing to do is to find the slope at the predicted value. So in this case, let's change to a different color here. Use red. Maybe I use something else. What color should I use here? I use blue. Okay, maybe let's use green here. Okay, so now I have my yi plus 1 based on our predictor. Now the next thing is that I know this is my predicted value. So the second thing to do is to make correction at the predicted value. So this is the one. So this is the corrector. Note that I need to make correction at the corrected value. So in this case, I need to find the slope here. I need to find the slope. So, okay, this is the slope. So look at this. This is my slope at x based on xi, y, I. Right? And note that this is the slope at fxi plus 1. Note that at this point here. So yi plus 1. So note there are two slopes here. There are two slopes. two slopes. So this is at the initial value. This is at the predicted value. So if you look at this one, what is this equation about? First slope, second slope, divide by 2. So what is this? What is this? What is that? Can anybody tell me what is that? You have two slopes value. You have two slope values, and you divide by 2. So what is that? I think you learned this before. What is that? What is that? Anybody? Anybody home? Nobody home? Anyone? If I have two values, for example, 2 and 4, and I divide it by 2, 2 plus 4 divided by 2, what is that?
Is it average, Doctor?
It's the average value of the slopes here, right? So basically, we are trying to improve the slope estimation by taking an average slope value based on the first slope, which is this one, which is the red one, and the second slope, which is the green one. So we take the average of these two slopes and use that to predict our new yi plus 1. So in this case, we say, okay, we corrected the value, okay, yi plus 1 equal to yi plus fxi yi, this is the first slope, plus fxi plus 1 at the new location, yi plus 1 divided by 2, and everything is timed with h. So note that this is the average slope. So the average slope might look something, I don't know. So you take this slope plus this slope divided by 2. So maybe, okay, maybe, I'm not sure how the thing look like, but okay, if you take a look at the next slide, okay, so this is the slope based on the first point, and this is the second slope based on the second point, and we take the average, so it might look something, maybe this is maybe it looks something like this. Oh no, I'm not going to use green here. Let's use something else. Okay, let's use a different color. Let's say I'm using this one, pink. Okay, so this is the average slope, for example. So average slope, and take a look at these at the results here. At the result, this is in your textbook again. So take a look here. This is Euler's method at h equal to, I think, 0.5, if I'm not mistaken. Okay. Euler's method, h equals 0.5. Now this is Hewan's method, h 0.5. Can you see the difference here? How much we improve from using the Euler's method? So this is the idea. So as you know, remember that yi plus 1 equal to yi plus fx I yi h. This is the Euler method. And again, by improving slope estimation, we basically improve our approximation. Okay, this is from your textbook, and I hope you can see that this is a much better approximation than Euler's method. Okay, so this is the idea. So of course, we cannot do anything else with h because we are done with h. So the next thing to do is to improve. is to improve. So this is the idea here. This is the idea. So basically what we have here is we use, for the character, basically we use average slope. Okay, average slope, which is the average of xi yi plus fxi plus 1 yi plus 1 divided by 2. Okay, this is the average slope. The predictor, we just use the first slope, which is just fxi yi, which is just our Euler's method. Our Euler's method. So basically, if you look at this is the first slope, this is the second slope. So maybe if I draw this is the first slope, this is the second slope. So the average might look something like this. Okay, the average might look something like this. So it is not as steep as the first one, but not lesser steep than the second one, because this is the average. So this is what we get. Okay, this is what we get. So this is the average slope. Okay, slope at the first point, slope at the predictor point, Okay, so this is what we call only one cycle, one cycle Hewan's method. Take a note that in here, it has a 0 here, and it also has a 0 here. So for now, I think you can not worry about that one yet, because this is what we call only one step Hewan's method. We can redo this multiple steps. We can predict multiple steps. So for now, the idea here is only one time. Once you get the once you understand how to do it only for one time, then you can repeat it a lot more times. So for now, let's not talk about that one yet. So I hope you can see that my point here is to show you there are two ways of improving our approximation. I think the first one, I think if you recall earlier, I said the first thing in numerical method is to estimate. The second step is to improve the estimates. So for Euler's method, there are two ways to improve. One is to reduce h, reduce the step size, and the next one is to improve the slope estimation. So this is one step. This is one method of improving the slope. So we take the average slope. The average slope of the start point and the predicted point, the initial point and the predicted point, and use that to estimate our new yi plus 1. So this is the idea. Okay, this is the idea. So again, what I'm showing you here is not the math. I'm showing you the idea first. So we translate the idea into mathematical equations. Okay, this is what I'm trying to tell my students. If you understand what is Hewan's method, the equation will come automatically to you. Okay, if you memorize the equation, then you might not get the full understanding. All right, so next is, okay, I showed you the how much improvement that Hewan's method can give to you. Okay, the next one is, okay, so this is the cycle. This is the cycle of Hewan's method iteration. So what I just showed you is one step Hewan's method. One step Hewan's method. Okay, let's talk about multiple step or multiple iteration. So if we do multiple iteration of Hewan's method, okay. Okay, multiple steps, multiple iteration. So let's say, okay, this is my xi, this is my yi. So we can use multiple steps here Okay, for example, okay, this is our predictor and this is our character, right? So we get our corrected yi plus 1. And we can do the same thing here to find another. So this is what we call y naught I plus 1. So this is the first iteration, y plus 1, the first iteration. So based on these two, we can find the average. So now maybe the average is this. And this is our predictor. Then we can find the new slope. This is y2i plus. And then based on these two, we can find the average. So we keep repeating this over and over and over. And you can see that it will be, your result will improve much better, much better. So this is what it meant by, Hewan's method iteration. So this is our initial point. So we get our corrector, and then this is our second slope. And based on the first and second slope, we get the corrector or the corrected slope. But note, this is only y0. So if we do the same thing again, then this becomes y1. So we keep repeating this. And then this becomes y2. So it has no limitation how many times you want to do it. So take a look at this. Take a look at this. This is Hewan's method iteration. So what I just showed you is only one iteration. And you can see that, of course, this is the initial condition. So y true is 2, y Hewan is true. Okay, and y Hewan 15 iteration. 15, you repeat it 15. So what you get is the first average is yi plus 1 and y naught I plus 1. And the second one is y naught. The second one is, this is the first iteration. The second iteration is the average of yi plus 1 plus y naught I plus 1 divided by 2. And then you get y1 I plus 1 over 2. So, no over 2. So this is the second iteration. And the third iteration will be this one. This should be y naught. Y naught I plus 1. Okay, and this is going to be y naught I plus 1 plus y1 I plus 1 divided by 2 and so on. So if you repeat 15 times, you can see that at, okay, for example, this one, 10.62, when x equal to 4, this is only 3.18. So it shows that it can be a lot more improved. But again, the issue here is that you have to do a lot of calculations. So this is only one iteration, but this one is 15 iteration. So the question here is worth the effort and time? Okay, is the extra calculation worth the effort and time? That is the question that you need to think about. Okay, so that's the first thing. So should I do 10 iteration? Should I do 15? Should I do 20? Or should I just do one iteration? Okay, so this is the question that you need to think about. You need to think about. So that's the Hewan's method. And the next thing to do is what we call the midpoint method. So we have talked about Euler's method, which is just the basic approximation. And we talk about Hewan's method, which is an improvement to Euler's method by improving the estimation of the slope. Okay, by improving the estimation of the slope. Okay, so the next one is the midpoint method. I think I mentioned in this class, we'll talk about only two methods, how to improve Euler's method. So Ewan's method, this is one, we talked about this before, and the midpoint method. The midpoint method. So how does midpoint method improve our slope estimation? Okay, so again, this is another way of improving slope Okay, let's wait for a while. Okay. Slope estimation. So Hewan's method, basically taking the average. Okay, taking average the initial slope and the predicted slope. So this is what we call the predictor. We predict first, and then we correct. We predict the slope, and then we correct the slope. How do we do the correction in Hewan's method? We take the average of the two slopes. Okay, so the midpoint method is basically taking the slope at the midpoint. Okay, for example, we know that this is our xi. This is our xi. And this should be our xi plus 1, right? So if you recall, Euler's method will take the slope up to this point here, right? But for midpoint method, it is not taking the slope at the predicted point, but at the midpoint, at half of the interval. So take a look at this. Instead of taking, we know that this is h, right? But the midpoint method is taking the slope at the midpoint. So this is h over 2. H over 2. And this is the slope. So how do we do this? How do we get the slope there? So take a look at this point here. I plus half, yi plus half. Okay, so basically this is telling us taking the slope at h over 2. At h over 2. So how do we do this? How do we do this? How do we do this? So it is just okay, so this slope, okay, let's talk about again the idea here. So we are not using this slope to predict our new point, but we are using this slope here. So this is why, okay, note that this is h, but the slope here is the one that we are using for the midpoint, I plus half, yi plus half. So basically in this case, we can see that our yi plus 1 equal to yi plus f xi plus half yi plus half times h. Note that this is the slope at midpoint. Okay, so that is the midpoint method. So this slope here is this slope here. Okay, so that's it. That's the idea. So the idea between these two methods, the Hewan's method and the midpoint method, is to improve our slope estimation. Okay, so how do we calculate? How do we calculate? So how do we calculate f xi plus half and yi plus half? How do we do that? Okay, so note that just now, Okay, this is h, right? But we are not going to calculate slope at this point here. But we are going to calculate slope at this point. So this is just h over 2. So what we can say here is that y I plus half, which is this point here, y I plus half is equal to yi plus f xi yi times h over 2, because this is h over 2. Okay, so you can see that now that it becomes yi plus 1 equal to yi plus f xi plus half yi plus half times h. Okay, so this is in the slide, but I think, okay, so this is wrong. This is not t, but this is xi, xi plus 1. So this is the slope here, right? This is the slope here. So this is h over 2. And this is this point here. So our h over 2. Okay, so this is how we calculate the slope at midpoint. Slope at midpoint. Okay, so this is how we do it. This is how we do it. So basically, we explored a few methods, how to improve the slope estimation, the slope estimation. And so we took the average slope in Hewan's method. We took the slope at midpoint in the midpoint method. Okay, so we also have one more general method. We also have one general method, which is this one, RK method, Ranga Kata methods. Okay, note again, this is the equation that we use, except now this is our slope estimation. Because there's nothing more we can do with our h, right? We make h smaller, but nothing else that we can do. So the only way to go now is to improve our slope estimation. Our slope estimation. Okay, this is similar. This is similar. If you look at this format, this is what we call the RK equation. But if you look at the general equation before this, the Euler's method plus fxi yi h. Note that this is the slope as the slope, right? So RK method basically is trying to improve the slope estimation. That's it. So we have seen Hewan's method, which is taking the average slopes, and we have seen the midpoint method, where we take the slope at the midpoint. Okay, and h here is what we call the step size. Step size. Step size. And take a look at this. This what is this? Phi. This is the increment function, and we have a1, a2 until an. So a equal to constant and k equal to this. Note that for our slope estimation here, it involves the x and y and also our h. Okay, there are 3 parameters when we are using the increment function. Okay, there are 3 things that we need to use. So in this case, you can see that we have our xi, we have our yi, and we also have our h. Okay, so I want you to read this on your own. 25.29. This is equation 25.29, which is in chapter 25, chapter 25. So RK method, we have a lot of RK method. So we have RK1, which is first order, with RK2. Of course, we have RK4. RK4. Okay, so RK1 is just Euler's method. For example, if you take a look at this, maybe I can show you later, but I think this is in my video. This is in my video. RK1 will become to Euler's method. So, okay, Euler's method, and RK2, okay, RK2, okay, this is first order Euler's method, first order RK method is equivalent to Euler's method, and second RK method is equivalent to, depending on the parameter that you use, it can be Schwann's method. It can be Schwann's method. It can again become midpoint method. And one more, which is not covered in our slope improvement, which is Ralston method. Okay, so now I hope you can see that why is Schwann's method much better than Euler's method? Why Schwann's method is much better than Euler's method? You can see that Euler's method is just RK1, which is a first order method. Schwann's method is RK2. Again, this is back to our, remember we talked about our numerical differentiation. Okay, I said that for your assignment number 8, you need to use second order accurate, second order accurate, because we use a lot more terms in our Taylor series, okay, in our Taylor series. So again, in your polynomial, remember your interpolation function? The more point we use, the higher the order, right? The higher the polynomial order. And because we are using higher order polynomial, the error becomes lesser. So this is the same idea with ODE. Higher order method produces lesser error than lower order method. For example, you can see that for Euler's method, which is RK1, the error is huge. But when you do Schwann's method, which is a form of RK2 method, second order, then you can see that it is much better than Euler's method. The solution is closer to the true solution. And of course, there is one more that I said just now. For RK method, there's one more that we have RK2, and definitely we have RK4, which is fourth order method. And definitely for our practical purposes, RK4 is good enough. RK4 is good enough for our use. RK4 is good enough for our use. So I hope you can see there are two methods so far which is important in our class. First is reducing our H for our integration, for our differentiation. Smaller H give you better results. Okay, the same thing with ODE. You can see that smaller H will give you a better results than bigger H. And then we can see that the order of the polynomial that we use, for example, in our differentiation and our integration. Remember, we have rectangular rule, which is using a naught, just a constant. Then we use trapezoidal rule, which is using a first order, which is a naught and a1. Okay, a naught and a naught plus a1x. Okay, a first order polynomial. And then we use 1/3 Simpson's rule, which requires a naught plus a1x plus a2x squared. And you can see that the result of the integration is much better than just using our trapezoidal rule. Okay, so this is the same thing here. This is the same thing. We improve the slope. Okay, so it so happened that when we improve the slope, this is similar to what we call the RK method, the Rangakata method. So RK method has a lot of orders, RK1, RK2, RK4, and of course, I think there is also RK3, third order, but the people always use RK4, because some ODE is not easy to solve. So we solve it numerically. I think I'm going to stop here. And be prepared to receive a new assignment on ODE, a new project for project 2, because today is the due date for project number 1. I think that's it. Okay, I think that's it. So I think this will end our session. So before we go, any question? Do you have any question? Okay, if there's no question, then we can stop here. And I think I see you again on Thursday. Okay, thank you, everyone.
Thank you, Dr.
Thank you, Dr.